Hello everybody, hope you're having a good day. Today we're going to be learning about the merge sort in Java. We're going to be doing this recursively, or in other words using recursion. And if you don't know what recursion is, I'll explain briefly in a moment when we get started. So the merge sort is a very fast sort, time complexity wise, and it does have some flaws, but it basically makes up for them with its speed. So also with the merge sort, we're going to be using the merge algorithm, which is basically the main part of the merge sort. This algorithm basically sorts the array. But what it basically does, it gets two arrays that are sorted and merges them into another sorted array. So that's very important with the merge sort, which I'll be explaining in a moment. So hope you're excited, and let's get started. Okay, so first let me start off with explaining recursion. If you already know what recursion is, then you could skip ahead. There'll be a timestamp on the video somewhere, so you can just go ahead and skip to the part where I start explaining the merge sort. But for those who do not know what recursion is, let me try to explain it in simple terms. So let's say we have this job right here. We could obviously do this all together, right? We could just do it at one time. Or what recursion is basically you take a certain job, like let's say this was our job, and you split it. So let me draw that out. So here you would split it. So I'd give, let's say I'd split it in half. Let's say this is half of the job, right? So this is half of it, and then let's say this is the other half of it. Okay, and that's basically, in simple terms, that's what recursion is supposed to do. What you're doing is you're taking this job that you have. In fact, let me change the color. So you're taking this job that you had, right? You had this job and you split it, and here you get these two more jobs, so they're basically half of the original job, right? So when you get these, this is easier to do, right, because they're separate. What we call them is, we call them stack frames. So each one is a stack frame. So when you split, you get a stack frame. Sometimes when you're doing recursion, there's a main, well, not sometimes, but the main rule of recursion is that even though you're splitting, you need to have a terminal case. So you need to have something that in the end you're like, okay, so then at this point when we split it even more, right, into two more stack frames, let's say here as well, two more stack frames, right? So when you do two more stack frames, let's say this was our terminal case. So basically what we're saying is, what I mean by terminal case, in fact, when you get another color, what I mean by terminal case is that at this point our work is done. You don't need to split another two, or you don't need to split into more stack frames. So that what this means, when it hits the terminal case, what it does, the recursion does, it will rewind back. So it will go back here and it'll become the half thing. So this job's done, so it'll go back to the half of the job, right? And it'll rewind back, and so now here half of the job is done, and it'll also happen from here as well, from the other stack frames that were created from the original. So it will basically rewind back, and at the end your job will be complete. So that's what recursion is doing. So we got to remember, you got to have a terminal case. Always have to have this. If you don't have this, you'll see an error called stack overflow error, and that's basically saying that there's no terminal case, so it doesn't know when to end, so it's going to keep going. It's going to keep going. So we need to have a terminal case, and we also need to have some way to call other stack frames. So how we call other stack frames, right? Let me just write this terminal out, right? Okay. So how we call other stack frames is actually we call the method that is doing this job multiple times inside this method. So if you think, okay, so what basically I'm saying is, let's see, so let me try to explain this better. So let's say I had this method called me or something like that, right? What we do is, inside the method, like let's say this was our method and these were the curly braces. I know these look really bad, but I'm trying my best here. Inside this method, we call this method again. So this method name is me, right? So inside of it, we would call me again. And usually when we're doing recursion, we have a lot of parameters here. So we'd pass different parameters so we can break this job in half. Like let's say we had a first and a last. We would find a middle, and then we'd say we'll do a first stack frame call from first to the middle. And okay, so let me write that out. Just imagine the F is first and M is middle. So we do a call from first to a middle, and then we do another call after that with same again, calling me again, right, the method, and then we're doing from middle plus 1 usually, because we already accounted for the middle in the first till the last element. So what this would technically do is basically do this. It would split it in half every single time it went into the stack frame. So this would be a fourth of the job, and we would also need to have, and so as I said, this would be a fourth of the job because we'd keep calling the stack frame. So every time, so let's say we call this again, right? Then we're basically getting first and middle as our first and last if you think about the parameters, and it would call this again. So then it would split again in so it'd be 1/4 in this case, right? So here, as you can see, this is where the terminal case really matters. So what this terminal case is basically needed for is if we don't have a terminal case, some case where we break or not break, we return. So that means it would wind all the way back. If we don't have this case, then it's going to keep splitting forever, and we're not going to get our job completed. So let's say we had like a terminal case that was like, I don't know, if first was equal to something like 1/4 or something like that. No, that wouldn't work here, but I'm just giving an example. Then we'd basically, if we give something like if first was 1/4, then you'd return. So that's when it knows, okay, I don't need to split anymore. I can just return the keyword, we'd use return, and return all the way back. So then it would just go back, and it would go back to the original job, and this would be completed. So that's a brief overview of recursion. So let's now get started with the actual merge sort. Okay, so let's get started with the merge sort logic. So first, let me change the color. So we get an array, right? As you can see, so this array is clearly not sorted, right? So now we use recursion, as I mentioned before, divide and conquer. So what we want to do is we want to split it apart. So what we do in merge sort is we get the middle part. So in this case, middle would be down here, right? And then we call a stack frame. So basically we call the method, and we do what we do is we have an I here, which is the first, and first and the last, or J we could say it, right? What we do is we calculate the middle value, and then we call a stack frame from the first index to the middle index, and we call another stack frame from middle plus 1, so this index to the last index. So what that turns out to be is it splits up here. So even though it doesn't look like it's splitting up in the diagram, what would realistically happen is these two would now be separate stack frames. So basically now our job was split in half. So here I have to rewrite all these, right? So our job is split in half. No sorting has happened here, but our job just split in half, like with recursion, right? So our job split in half. Again, here we don't have to do any sorting. This is the actual. I'll explain why we don't do any sorting. So here again, we calculate the middle value again of each stack frame. So for the first stack frame here, as you can see, this would be the middle value. And for another stack frame, the next stack frame, it would be this value. So we split again at this value. So now we actually have 4 stack frames going on in basically one program. So here's 4 here. So let me show that actually. So this is one stack frame. I'll do another color so you guys can tell what each stack frame is, right? This is another stack frame. 1 and 5 is a stack frame. 2 and 3 is a stack frame. And 8 and 7 is a stack frame. And here we don't sort either. We again split in half. Okay. So here each stack frame has their own half. So as you can see, the orange here, that would be another splitting point. So now at the end we actually have the same amount of as we have. Basically all the elements are in their individual stack frame. So 9 is a stack frame, 4 is a stack frame, 1 is a stack frame, 5, and so forth, as I'll write these elements out, right? So they're all in their own stack frame here. So now here we can't really split in 2 again, because obviously if we split in 2 it's going to be the same element, so there's no point here. So as I mentioned in my recursion explanation, we need a terminal case for recursion. So in this case, this would actually be our terminal case. So what we'd actually do is we'd check, as I mentioned up here, we would have like a first element, which we could say first variable, which could be I, and J could be our last. So we'd actually check when I was greater than or equal to j. Well, most likely when it's going to be equal to j. So here in this case, this would be I, and this would also be j because that's our last of our stack frame, right? So the I and j are the first and last of the stack frame. You got to remember that. That is actually very key. I and j are the first and last of the stack frame. So you know how we split here, we split in the middle? What we basically did was the j, I and j. So this was the I and j for this stack frame here. As you can see, this was the I and j for this stack frame, this 4 element stack frame. So you got to remember the I and j is the first and last of the actual current stack frame, or one stack frame. So here, as you can see, this would be our terminal case. Now this is where the sorting happens. This is where we use something called the merge algorithm, right? So let me explain what the merge algorithm does. So the merge algorithm, right, is basically when you get two arrays that are sorted, or two parts of arrays that are sorted. So in this case, let's think about it. So we see that we have each of these stack frames. They're basically each individual element. So technically, we can use the merge algorithm because, as I said, that they have to be sorted. And technically, if it's one element, it's clearly sorted. There's nothing else that we need to sort with, so it's clearly sorted. So what the merge algorithm does is takes two sorted arrays, or two sorted parts of arrays, and it merges them together, as hence the name, right? So it basically takes these two elements. So in this case, we'd have 9 and 4, right? We compare these, right? We got two parts, and we basically merge them back. So this is where, when I said we return and we get rewires back, or rewinds back, that's when we call this merge algorithm. So what it does is it takes these two parts, so in this case 4 and 9, and it merges them and it sorts them at the same time. That's why this algorithm is actually very powerful. You take two sorted arrays, and I want to really emphasize this. You take two sorted arrays, or two sorted parts of arrays, and you merge them, and at the same time you're sorting them. So in this case, when we rewind back, right, my diagram, I'll explain this way. So it'll go like this, and it'll go up like that, right? So you merge these two elements. So what are we gonna get? We're gonna get 4 and 9. And as you can see, we basically merged these two back, and we got 4 and 9. Okay. In fact, let me actually draw that out. It might be more clear that way, actually. So we had 9, 4. I'll just write out all the elements just so I can show the actual rewinding back, so it makes more sense. So we have this basic right here, right? So we want to merge these. So these are two separate parts of the array. So what we want to do is we want to merge them right here to this two. Like just as how we split, we merge them back into that basic, like that range. So what we're doing is we're merging and we're sorting. So what would actually happen is, now, remember at this point we were splitting these two here, right? But now we're merging them back. So this is the stack frame returning back. So it's rewinding back, just like how recursion works. And it's sorting at the same time, which is being done through this algorithm right here. Same thing here. We're going to do the same exact thing. We're going to take two parts, right? And we're going to merge them. So we're obviously going to rewind. And as we rewind, obviously these two are already sorted, so they're just going to go like how they're supposed to be, just normally. Again, same step continues. So actually, if you see and if you realize, none of the sorting actually happens when you're actually breaking it apart. Nothing happens there. You're just breaking it apart. The sorting actually happens when you hit the terminal case and it decides to rewind back. That's when you call this merge algorithm, and it will sort everything for you. So at the end, like I explained, your job will be done. In this case, our job is to get it sorted. So let me finish this out. So as you can see, we merged these. These are also sorted in order, so they just go back like normal. So 2 and 3, and then last 2. So 8 and 7, we merged them. So now these are going to get sorted because they're clearly not in order. So now 7 is going to be here, 8 is going to be here. Okay. So as you can see, that's what we're doing. When we rewind back, we're merging them. So again here, these are, now we see that when we split the 4 into 2, now we are back into the same stage. So we merged those. So now we actually have to merge these 4 elements instead of back here when we were doing 2. So now we merge these 2. So what we get is, so we have to merge this part right here. Let me explain this. This part, okay, actually that was bad. This part of the array, and this part of the array. So we merge them right there. So there's going to be a split at this because it's going to be just like how we split from 4 to 2 right here. So we're going to merge these, and as I said, when you do this, you merge them. So you basically put them in like one stack frame, like return as one stack frame, right? But they also get sorted. So what in this case would happen, 1 would come to the front, 4 would be the second, 5 would be third, and last would be 9. So as you can see, they're all in sorted orders. This stack frame, when we split here into 2, remember that when we split into 2, now it's back here and it's sorted perfectly. Again, we'll do the same thing for the other 2 stack frames. So we take this part of the array and this part of the array, and we merge them right back. Merging, basically putting them into one total array, right, or one part of the array. We're basically completing the parts, right? And here in this case, it's actually sorted for us already, but it's still merged like it's supposed to. So it'd be 2, 3, 7, and 8. Now here, remember, we split the entire thing into 2 parts of 4 because we had an even number, but in the odd numbers it would also work fine if you were wondering that. But here in this case we had 8, so we split into 4. Now we have the 2 stack frames back to like how they were when we first divided. So we have these 2, and now we take both of these parts of 4 and we merge them back into the entire array. So when we merge here, we'll have the completely sorted array. So what will happen is we'll get 1 here, we'll get 2, 3, because remember that this merge algorithm is taking care of the sorting for us. So we'll get 1, 2, 3, 4, we'll get 5, and then we'll get 7, 8, and we'll get 9. So as you can see, using recursion, let me just overview this. So overall, as you can see in recursion, we split it apart first. We keep splitting apart in half and half until we get to the part where the part of the array is just one element. When we hit that part, we say that's the terminal case because there's no need to split anymore. When we hit the terminal case, we'll rewind back, we'll return. So we'll rewind back, and when we return, we call this merge algorithm. And this merge algorithm is very important as it takes 2 parts of the array and it merges it into one, like it combines them basically, and it sorts them at the same time. So that's how our 9 and 4 became 4 and 9, 1 and 5 became 1 and 5 because they were already there and it still merged them. Now 4 and 9, 1 and 5 became this in sorted order. And as it rewinds back, as you can see, every stack frame, it rewinds back, and at the end, our job will be done. And that's the main point of using recursion for this. So I explained the merge sort. Let's basically go over to the code and actually write. Okay, so let's get started with the code. I'm using Eclipse for the code here, but you can choose whatever text editor or IDE you would like. And I just went ahead and made a class called merge sorting, and I also just put a main method. And I used the same array that I used for my drawing, so it's the exact same array. So let's get started. So I'm going to make a static method, call it merge sort, and we're obviously going to need the reference to the array. So I'm just going to call that reference name and that variable name data. And as I said, we're going to need a first or a low and a last or like a high variable, right? So I'm going to say int low and int high. And so here we got our method. And just so when we want to print it out to see if it actually works, I'm just going to create a print array method right now so we don't have to worry about it later. And I'm just going to do the simple, just print out all the elements in the array. So like that. So all we're going to do is just print out every single element and just give spaces between them so we can just tell if it's sorted or not. Okay, so let's worry about the actual merge sort method. So as I said, we need to use recursion. So we're going to call this method over and over again. And as I said, we're going to split. We're going to split every time in the middle. So we should first calculate that middle. So what we need to do is we need to make int middle, and we're just going to do the middle. So we're going to find the index middle, right? So we're going to do that. Low plus high divided by 2. Basically, we're taking the lowest value and highest value and finding the middle by dividing it by 2. So that's how we'd find the middle. And now what we need to do is we call this method again. So as I said, we're going to call stack frame. So we're going to split in half. So we got our middle value. So we need to call 2 stack frames from here. So again, we pass this data, or we pass the array. We pass low, which is still going to be the lowest point, and we're going to pass middle now. What that means is this stack frame, or this method, next time when it gets called, it's only going to go up till the first element, or which we're going to pass in, till the middle, or the lowest element to the middle, which we calculated here. And again, we need to call this method. Now it's gonna handle the other side of it. So middle plus 1 till the high value, so the last value, or last value in the range of the array, like I was saying in my diagram. Now see, now here we just got our splitting. Our splitting is done. So when I was talking about on the left side, we were talking about how we need to split into half until we get to a terminal case. Now we've taken care of the splitting, so that's the splitting part. But here we need our terminal case. So what our terminal case will be, as I said, so I said when it gets to one element. So we can really check that with when low is greater than or equal to high. So basically when it's ever equal to high, we're just going to return. So we know we don't need to split anymore, so it's just going to rewind back. Now when it rewinds back, it will not call this stuff, because so it works up, the method calls are going to work this way, right? So up from, like, each code, it will be up and down, right? So this stack frame will finish and it'll be returned back, and this stack frame will finish and it'll be returned back. So any code that we write after this, it will actually occur, or will be ran when the stack frame actually returns. So when it's done with splitting. So here is where we should actually put the merge algorithm. Okay, that's where we actually need to put the merge algorithm. So how the merge algorithm works is you need 3 variables. Okay, so we're going to merge 2 parts of the array. So I'm going to create an int I variable, which is going to be our low variable, and I'm going to create int j variable, which is going to be basically our middle, or it's actually going to be our high variable, right? And actually, no, never mind, I was right. It's going to be our middle plus 1 variable. So basically the lowest value of the second part of the array, if you think about it, right? Middle plus 1, like how we're doing that here, middle plus 1. And we're going to need a k variable, which is going to be our low variable. So the k is going to be, let me explain this. So I is going to be the current, like the current part of the array, or current lowest value of the array. So let's say we were merging 9, 4, 1, and 5, and so basically our I would be the 9 index, and our j would be the 1 index here, so middle plus 1. And what our low would be is, so I remember when we had those 4 spots open, we were merging these 2 into those 4 spots. The k would be, so it would be the 0 index, or the first index of this actual 4 spots, the empty spots technically, right? So that's what the k would actually be responsible for. So what we actually need to do now is we need to check if I is less than middle. So we don't need I to actually go past the middle, which you'll see because we're going to do incrementing. We're going to increment I, and we need to check if j is less than equal to high. So basically now we're just making sure nothing's going out of range, right? That the out of range where it doesn't need to go to. So now what merge algorithm does is we check the element at low and the middle plus 1, so element at I in this case and j, and we compare those. And if we find I is actually greater than j, then we put the value at j at k. So what we're basically doing is we get, so again, I'm going to use the same example, 9, 4, 1, and 5, is that we're checking if the value at 9, or I, or value at I index, which is 9, is if it's greater than the value index at j, which is the one where the 1 exists. What we're going to do is we're going to take the 1 and we're going to put it at 0. So let's imagine these zeros were the 4 empty spots that we had, that we were trying to merge into. So what we're going to do is we're gonna take the 1 and put it at k, which would be this part, the low variable. So what we'll actually get is we'll get 1 here, 0, 0, and 0. So we basically merge the 1. So this is how actually the sorting happens while merging. So how we do this is we basically check if the data at our I variable, as I said, is greater than the data at our j variable. So if it is, then we do data at k equal to data at j, because that's the lesser value or the smaller value, right? And again, in the other way around, if the value at j was actually greater, so let's say we were at 4, let's say our I was at the 2nd index in this case, and j was here at the 5 index, what we'd see is, okay, so data at I is actually less than j, right? Data at j, so we'd actually put the 4 here instead, so the 4 would be here, right? So that's what we need to do. So I can just put this in an else because there's no other cases like that. So what we're going to do is data at k is going to be data at I. Now this will actually not work here because we're actually missing one thing. We need to actually increment these values. So we could do it like let me show. We could just do it like this. So we basically do k plus plus, and then we do j plus. We increment j plus plus because we want to check after this, because we don't need to deal with this value anymore, right? Because we already put it in. So we just do j plus plus. In this case, it would be k plus plus, and I plus plus. But there's actually a better, cleaner way to do this. So this actually requires you to know post and decrement operators. So what I'm basically saying is we can actually reduce the amount of code that we need, and we can put k plus plus and j plus plus in here. What this plus plus after the variable actually means is that first get the value that was already there, so it will do all the swapping thing that we had, or well, not swapping, the putting where we took the j value, put it in the k. It will do that, and then after it's done with that, it's going to increment. That's what k plus plus is. But if it was plus plus k, then this wouldn't work, because then it would actually increment the value of this variable, and then it would do all the putting and stuff like that. So that's why in this case k plus plus and j plus plus works, and we do the same thing here as well. Okay, so now we're actually sort of done. But let's say in one case, let's say in an odd case, like there are odd elements, then that means that in one case I or j will be out of the range, but the remaining elements will be left over. So in this case, we only need to check if I is less than equal to middle. You might be thinking, okay, what if j is out of range, right? Let's say we keep incrementing like how we increment, but then we see that, oh well, j is already out of range. Well, we don't actually need to account for that, because that means, since we're sorting, if j is out of range, which is actually these parts, right, that means we know that these must be the highest or the biggest or the largest elements in that like array, right? So that means if they're the largest elements, I know here in this case we have zeros, but then in other cases this would actually be the numbers, like the actual original numbers that were there before, because we're only acting on that array, right? So then that we know that these are actually the largest elements. So then they're already actually technically be there, and you'll understand more when we actually write it, when you see the output. But that means the largest elements are already there. You don't need to actually put them back in. So the only thing we need to take care of is actually the middle part. So what we're basically saying is, let's say you do this I++, and basically it's greater than the middle. Now it's going to be greater. We don't need to actually go on because we already split in stack frame, right? So then what we do is we do data at k, because we're putting it there, and then data I++. Okay, and here this should really be it. So if we were to actually run this, right, you will see that, okay, and we have to give that length, right, -1, and we have that print array method here. So I'm just going to pull this up right here so we can see it, and we pass the nums in the variable, so now we are the array so we can print it out, and you'll see, well, what happened here? Well, as you can see, it's clearly not sorted. In fact, some of the elements seem to be like overwritten. So this is another key part of the merge sort, and it's also probably the biggest flaw of the merge sort. This is really actually happening because we're making these merges into the same array. You know how we were talking about how the merge algorithm, it merges two different arrays, right? But you can also do two different sections. You can also do two different sections, but in this case, when you do two different sections, it's actually overwriting some of the values. So like when we're checking for these values, like if I is less than j, well, technically when we're putting this value in, j is technically here, so we're technically overriding what we have. So in this case, like it would actually be 9 for, instead of how I wrote zeros, it would actually be 9 4 1 5, and we'd be merging this into that. So when we do that, we clearly check this, right? So then, as we said, 9 is greater than 1, so we would put 1 there. But then that actually becomes 1 4 1 5, and we completely just lost this 9. We don't have it anymore, right? So that is the reason we aren't actually getting, it isn't sorting for us. We aren't sorting. So that's the biggest flaw. So what the flaw, how to fix this flaw is, you actually, whenever you do merge sort, you have to create another array that is the exact copy of this. So I'm just going to create nums1, that's just, or nums2 actually, and that's the exact copy. So what we need to do is, instead of actually merging to the original array itself, we need to copy all the elements from, we basically need to copy all the elements and we need to merge to that. So actually, in fact, we can just make this a new int and then just say size 8. We don't need to actually write it out. We'll actually copy the elements here, so you'll see what I'm trying to say. So now we need to actually pass this as well. So data 2, right? So we're gonna pass this, and so basically we need this again. Let me just clarify. We need this so we don't overwrite our data elements that we have in here. As you can see clearly, it's overriding these. So we need this, okay? So again, we pass this in here as well. It's not really, when we're splitting, it's not really it doesn't really matter. But when we actually do the merge algorithm, it really matters. So here, what we do is, as soon as we make these variables, actually, even before, it doesn't really matter. We need to actually basically copy the elements from nums, or the original data, into data 2. So here, we don't actually need I to be 0, we can make I low, because we don't need to merge everything at the same time. We can just merge the parts or the ranges of each stack frame. So we can do that, and we basically say I is less than or equal to high, so we don't want it to get out of the range, right? And then we do I plus plus, and all we do is we make the data 2, and we're basically mapping the values that were in data into data 2, so we can actually use that for merging. And now all we need to do is we take the data 2 and we just put it here. So we need to only compare with data 2. We don't need to compare with the actual data. So now what we do is we keep the data k++, because that is technically our other array. If you think about it, in quotes, that's our other array that we're merging to, and we need to get the value from data 2, not from data, because if we get from data, as we saw, it just overwrites it. Same thing here and same thing here. So now if we were to print this out, you would see that, as you can see, our array is sorted. So that is the thing. It's the time complexity of merge sorting is actually n log n, so it's actually very fast. It's a pretty good sort, and it's very fast sort, but there is a memory complexity to it, and that memory complexity is that you need another array of the same size. I mean, in this case we're doing size 8 array, but if a size 1,000,000 array, you need to have another size 1,000,000 array. But even though it does take up more memory, it basically makes that up with its speed. So I hope you enjoyed this video and hope you learned something from this. If you like, please leave a like on this video, and please subscribe if you haven't. If you want any more videos like this, any other sorts or any other languages or anything else, any other content that you do not understand, please let me know in the comment section below. And I hope you have a good day, and see you later. Thanks for watching.